recording. All right, so for the second classic organometallic paper, this is synthesis of the first alkylidine species by Shrock, who is shown here at right. Happy looking guy, I would be happy to. If again, just like Heck from the first presentation, I won a Nobel Prize for my discovery. So his was about 5 years earlier than Heck's, whose was in 2010, so Shrock received his in 2005. This is going to be a little bit in contrast to some compounds that have already been discovered. So there are what were called Fischer-type carbines already in the literature at this point. As far as your kind of generic scheme for a Fischer-type carbine, carbine again means we're implying a metal carbon double bond, but that's going to be the same thing for the Shrock alkylidines. The difference is what they have hanging off of the carbon, as well as some properties of the metal involved and the type of reactivity that either one undergo. So in general, for a Fischer-type carbine, so this is an example from Cotton and Wilkinson, their Advanced Organic text, is normally you're going to have a carbon with some kind of heteroatom with an R group off of it. So in this case, oxygen is being used, but it could be, say, nitrogen, sulfur, or something else. The idea is that you have a pi system. My laser apparently just died. No? Don't want to show that yet? Come on. All right, my laser died. Anyway, so what you're going to have is basically an empty p orbital on the carbon to where you can either have double bond with the metal, or you can imagine having one of these lone pairs on the oxygen flip in and then flip out the lone pair onto the metal in that case. So you can kind of have a couple resonance structures that you can work with in this case. So this is kind of the overall bonding. You still have that sigma donation. So for the carbene, you're going to have your sigma donation into an empty d orbital, and then if the metal has some d electrons, it can force them back onto the carbon, or again, we can have donation from that heteroatom. So these were discovered way before Shrock's work. These were back in the 1960s when they first started coming. And features, generally it's going to be low to mid oxidation state for the metal. And normally we're talking about middle to late transition metals. So not really so much the early ones. In general, we have ligands that are capable of back bonding on the metal. So generally on a lot of these, you'll see a CO group or more, because we want to be able to suck a little bit of electron density off of there. And as we stated, normally we're going to have some kind of heteroatom off of that carbon on the carbene that's going to do some bit of pi donation if it can. So a couple examples of these. This is a rhenium compound. So we have a CP ring up top, 8 of 5. These are all from Marvin sketch, so they might look a little different than what you would get out of ChemDraw. So we have all the carbons bonding, so that's why we have the 5 lines, so that's showing 8 of 5 in this case. Oxygen heteroatom off of the carbene, and then we have that CO group that's possible for back donation. Another one is chromium carbonyl, where we have a carbene. In this case, the heteroatom is nitrogen. And the last case, we have iron. This one's a little bit strange with regard to carbene. We don't have a heteroatom. This is actually a carbene off into a strained ring, so kind of strange. But those are all examples of Fischer types. So this is going to be a little bit different as far as what Shrock has going on. Very few, so these were the only ones that were known at the time, very few of these guys ever are going to have a hydrogen coming off as an R group on that carbon. So these were the only 2 examples at the time. This is going to be far more common for the Shrock types. So the synthesis from Shrock's paper. We're taking lithium reagents, so very similar to what we do in lab as far as taking that in butyl lithium and using it as a reactive carbon species. This is going to be the same thing. So we're going to take 2 equivalents of that and react it with this tris T-butyl tantalum compound that has 2 chlorides sitting on it. So what we're planning on doing is having lithium bind with a chloride, crash out as a salt, and then this reactive carbon that's going to be nucleophilic is going to attack the tantalum. And so we're going to get generation, in this case, of a neopentane from decomposition of this molecule, and that results in the formation of this alkylidine species. So this is our starting species. We have those large, bulky groups, as you would expect, in the normal position. So what's our overall generic geometry that we would associate with this compound for a gen chem?
Trigonal bipyramidal.
Trigonal bipyramidal. So trigonal, we have 3 in the equatorial plane, and then we have these 2 axial groups. And so we can make a pyramid up top, pyramid on the bottom. The T-butyl groups are shown specifically in the equatorial plane because that's where we have the most space in this type of geometry. Remember, if we're at these axial positions, we have 3 90-degree interactions, which is worse than if we're in an equatorial position. We have 2 90-degree interactions and then 2 120. So we have a little bit more room on the equatorial plane. So that's where those bulkier groups are going to go. Unfortunately, when we strip away these chlorides, we're replacing them with 2 more of those super bulky groups. And the thought is that some of that steric congestion, as it were, is what leads to the decomposition and the formation of this alkylidine. So the idea is that we'll replace both of these guys with another CH2 T-butyl group, so hella steric congestion. Then we're going to have alpha hydride abstraction. So where we have these CH2 groups, here, here, and here, and then we would also have one on the top and the bottom, any one of those is going to be able to lose a hydrogen and then form this double bond with the tantalum. And when that hydride jumps off, it's going to form a neopentane. That's just going to go bye-bye into the solvent, and we end up with this reactive species, which is still relatively bulky, but less bulky than if we had 5 of those T-butyl groups surrounding it. So we go from a trigonal bipyramidal structure to one that's a little bit more similar to tetrahedral. So this is what is proposed as far as their mechanism. Again, fairly simplistic. We're going to take this pair of electrons from this carbon-hydrogen bond, flip that in. That's going to form our double bond between the carbon and the tantalum. And then this pair of electrons is going to jump off the metal and suck onto that proton, and that's how our neopentane is going to float away. So what they did as far as trying to discern that this was actually occurring was by doing a whole bunch of isotopic labeling experiments, which are always fun to do. So what they've done is, in their starting material, they've deuterated those methylene groups off of those T-butyl substituents. So that carbon that's directly bound to the tantalum was a methylene, it had a CH2. We've just replaced that with 2 deuteriums. Our lithium reagent, we're still using undeuterited. So the methylene unit from that is still going to be CH2. And what they end up doing with 3 different trials is running different mole equivalents. So this is the one that they directly reference in the paper as far as 1 to 2, because we want to get on those 5 R groups. Here they run one with a lack of lithium. Here they run one with an excess reagent. And then this is what they should get as far as the isotopic distribution based off of just statistical theory. So what these labels represent, whenever you guys see an italicized D, and if you guys, when you were making up your NMR tubes, Dave, I heard you ask Wakefield about it possibly. Whenever you see a little italicized D with some kind of superscript, that's representing the number of deuterium atoms that are in that substance. So when you guys saw CdCl3, the deuterated chloroform, it would have had a little D1 next to it. When you use acetone, it has 6 hydrogens that are replaced with deuterium, so you see D6. So what they're trying to show in this case is for that neopentyl group that falls off and goes into solution, is there no deuterium on that product? Is there 1? Is there 2? Is there 3? And then in the tantalum product, they're trying to see what the deuteration is at that alkylidine carbon, whether there's a deuterium on it. Now, I'll be honest, as far as trying to replicate where they got these numbers from, it's a little bit difficult, to be quite honest. I haven't had much success in replicating it. So I'm not going to pretend that I know where those numbers come from, but I'm going to believe that they did the statistical analysis correctly. And really what we're concerned with is being able to compare our theory, what they get from these numbers versus what they actually saw via experiment. So the idea is that based off their theory of using 1 to 2 equivalents, they will get a majority of the neopentane with 2-deuterium, and they will get a vast amount of that tantalum compound that has 44%. Now, if we compare that to their trial where they use that same mole-to-mole ratio, they get fairly good replication of these values. Pretty damn close, right? Now, they state, and this is kind of important if you didn't go into the methodology of it, they state that based off of how they do this analysis, which is when they get the reaction mixture, they separate out the neopentane, and then they inject that into a GCMS. And so what they're looking at as far as being able to assign these percentages is breakdown of the different deuterated neopentane compounds. So what they were able to do is they took pure D1, D2, D3 neopentane that they bought, subjected it to GCMS, saw the fragmentation pattern, and then they matched it up with what they got out of their product solutions in this case. So that's how they were able to generate these numbers. That methodology, they specifically state, has an error of plus or minus 3%, which makes these numbers that they get even better as far as, well, maybe this is up 3% to 41, that's a little bit closer, plus or minus 3%, that's within that range, plus or minus 3%, we're now within that range, closer within range, right? So that's something to mention just as far as how they're able to get these numbers. As far as these other 2 trials go, if they have a smaller amount of the lithium reagent, how that affects our numbers here, it looks like it doesn't really affect them all too much, to be completely honest. When they go overboard with the lithium reagent, it also doesn't really look like they affect the numbers all too well. And really what those 2 are getting at is the reaction rates that are involved in this process. So kind of the overall results they get from looking at these numbers are that neopentane is formed by the alpha abstraction from that mechanism that we all showed, and that all 5 of those neopentyl ligands are going to be involved as far as the statistical distribution of things go. They're going to say that alkyl exchange between the starting tantalum complex and the lithium reagent or any intermediate species that are formed is going to be slow. So this means that we're not going to have to worry about our product interchanging with any excess reagent that's out still in solution. That once we form our tantalum complex, that's really what's important. And they're going to say that our reaction rate between the tantalum complex and the lithium reagent, at least initially, is going to be our slowest step. And so once we form that tantalum complex, it's very quickly going to decompose and give us our alkylidine. So that's why they're saying that there's not going to be any exchange, because once we form that tantalum complex, it's very quickly going to decompose. It's not going to have a chance to exchange with any, let's say, excess lithium reagent, which is what they're saying as far as the last point goes. So what we have is our initial dichloride is going to react with 1 equivalent of our lithium reagent. And so now we have the monochloro species. I'm going to say that that's reaction rate 1. Take that monochloro species, react it with another equivalent, so now we have our 5 neopentyl groups coming up here. That's reaction rate number 2. And then the decomposition of this guy to give us our alkylidine complex as well as free neopentane is going to be reaction rate 3. Based off of those deuterium species, what they're saying is that reaction rate 3, this decomposition process, is extremely fast. This second step, where we're replacing the monochlorine with our last neopentyl group, is a little bit slower, and then this initial step is the slowest. So again, the idea is that once we get to this guy, instead of giving this guy any chance to do any type of further exchange with anything that's out in solution, it's going to go through this reaction pathway is what they're getting at. And that's backed up by what they got as far as their statistical parameters, as far as trial A versus what they had for theory, since those numbers were so similar. If the numbers had been vastly different, that would lead them to say that maybe there's some issues with exchange as far as on the time scale. That makes sense? Hopefully. So, in comparison to our carbines from earlier, this is now the Shrock carbenes, and so instead of being called carbenes, which I have the name up here, normally these are referred to as alkylidines. So carbenes more of an umbrella term. I did want to write up a couple things here. So just to recap the Fischer, we're going to have poor back bonding to the metal. We'll have pi donating R groups. And what I didn't mention before is that Fischer is treated as an L-type ligand. So you guys remember when we were first introducing ligands, we have the L-type versus the X-type. So the L-type is the neutral type, and then the X-type generally is going to carry some kind of charge. So when we think about the bonding in this case, as far as thinking about breaking this guy apart, we would think about the metal keeping 2 of the electrons in that double bond, and then the carbon keeping 2 of those electrons. And so this overall, as far as the ligand goes, would be neutral. The carbon wouldn't be charged, and so that's why we call them L-type. As far as reactivity goes, it's going to be electrophilic at carbon, which means it's going to carry a partial positive charge. So for our Shrock, I'm not going to write these guys back up there, but it's going to have our high oxidation state, early transition metals like tantalum. Normally there's going to be a strong amount of back bonding. And as far as the R groups go, alkyl groups, proton, hydrogen are going to be typical. Unlike your Fischer-type carbenes, we treat these guys as X2 ligands. So in the case of our breaking apart these guys, we're going to say that those 2 electrons that the metal kept in the Fischer case, it's going to give those to the carbon. And so formula, we'll think of the metal as having +2 oxidation state. And then the carbon will have 2 more electrons. And so it has that -2 charge, which makes it an X2 ligand. And so unlike the Fischer types, it's exactly ass backwards. So instead of being electrophilic at the carbon and carrying a positive charge, it's going to be nucleophilic and carry a negative charge. Let's see. As far as use goes, this is one application, so this is called TEBS reagent. This species is generated in situ between an initial titanium compound and then a trimethyl aluminum compound. So normally this has a chloro group, and then the titanium also has a methyl group, and then it decomposes and forms this compound. This can also then rearrange, spit out this aluminum, and we form this reactive alkylidine species. So titanium, just like tantalum, early transition metal, high oxidation state. So if we're assuming that these Shrocks are X2 type ligands, this titanium is all the way oxidized. So it's going to have -1 the CP, -1 the CP, -2 for the alkylidine. So this guy's formally +4. It has no more d electrons. These guys are fairly reactive. So what you can imagine is this carbon is partially negative, right? This guy, titanium, then is going to be partially positive. How this generally works is then you have some kind of external reactive species. So here we have a ketone. We know for carbonyls, oxygen is partially negative, the carbon is going to be partially positive. So this is going to come up as such, where the oxygen is going to want to interact with the titanium, negative wants to go with the positive. This partially positive carbon wants to match up with this partially negative carbon. And so what you end up forming initially is some kind of cyclobutane ring with a metal involved. And then that breaks down. You get spit out of titanium oxide material, and then you get what you want as far as conversion of that ketone to now double bond and alkene species in this case. So depending on what your R groups are off of that alkylidene, you can form different types of functional alkenes. I'm not sure if I have a different reaction shown here. So that's using this titanium reagent as far as showing kind of a similar reaction with our tantalum compound that we just drew up. And that's a good one. I'll try to show on the board instead of my hand waving. So our partially negative carbon, our partially positive tantalum. And then we have our partially positive carbon on this aldehyde in this case, interacting with our partial negative. And then our partially negative oxygen is going to interact with our tantalum. So we form that same four-membered ring, decompose, so we have our here, and we spit out an alkene group.
So it's like a baby.
Yeah, looks very similar. For, I guess the last thing, let me see if I can go back here. So how many, what's our total electron count for this tantalum species?
0.
So that's a d electron count.
Oh, you mean, oh.
So just as far as total number of electrons.
11? Are we?
I think it's 10.
10, yeah. So we'll have 2, 4, 6, and then 8, 10. Again, -2, -1, -1, -1. Tantalum only has 5 electrons, so it goes to 5 plus, so we're at D0 yet again. Last thing, as far as something I haven't mentioned structurally. So this only has 10 electrons around it. I'm not happy, right? So in almost all cases, if you're that low, the metal wants to do anything it possibly can to try to get more electrons. So what you will commonly see is that our ideal bond angles around this carbon should be what?
120.
120, if this was our normal sp2 guy. What we normally see for these types of alkylidene species is, since this is so electron deficient around the metal, it tries to get electrons from bonds. And so this is that agostic interaction that we've talked about. So what you normally see is this carbon-hydrogen bond is horrendously distorted from traditional 120 degrees. So this pair of electrons in this bond are trying to be donated into the metal. And so this thing ends up coming down almost to 90 degrees because it's trying to donate that pair of electrons in there. And so what you'll see as far as this bond angle between the metal carbon and then this carbon is something almost close to linear. It's really kind of jacked up looking, just as far as X-ray crystal structures look. So you'll see that a lot, and that's, again, kind of a common identifier that you can use as far as being like, oh, it's most likely this Alpilidine species because of this horrid distortion that's going on. So that's the last thing I wanted to mention as far as Shrock goes. Questions, concerns?
What do we care about the deuterium count?
So the deuterium count is basically to affirm their mechanism as far as what they saw based off of their actual deuterium experiment versus what it was expected theoretically. Confirms that the R groups come on relatively slowly, but once they're on there, instead of exchanging with any excess reagent, it quickly is going to decompose to get those statistical neopentane distributions as far as 1, 2, or 3. So it's just to confirm what they were seeing experimentally more than anything. Anything else? We'll see, we'll most likely look at one of the catalytic reactions involving this. Normally they involve those titanium species that were shown with the CP rings. In any event, we shall move on. What time are we looking at currently?
9:40.
Holy crap,
Oh, wow,
that
really?
hard on Shrock? Oh my God. All right, well, let's see how far we can get in Kubas. This one will be a little bit faster, I hope, so maybe we'll be able to finish. Just yell at me if we're running out of time. Is it better, Alex?
Where's the button?
As far as the title.
Oh.
I couldn't make a good one with Kubas as a name,
Doesn't
so
look happy.
we went with that. You wouldn't be happy either if you were that old. Come on now.
I'm not happy now.
Right? It only gets worse, David. All right, so Kubas, the white-haired gentleman shown here, I'm basically looking into my future.
You're already white.
My mirror, right? This guy, slack ass, did not win a Nobel Prize. Come on, Kubas. But what he did do was a lot of structural characterization. Obviously, his is the first well-characterized eta-2 coordination mode for hydrogen. And so he ended up doing a lot of research with these types of materials, and so this is a book that ended up getting published as far as kind of encapsulating all of the papers that he had written on this subject. So before we get into it, a lot of the structural parameters come from X-ray and neutron studies. And up to this point, really structural, I keep trying to use the laser, structural parameters for these hydride species, not even the eta-2 coordination mode, but just for the eta-1 coordination mode, really didn't start coming into the literature until around the 1960s when X-ray and inelastic neutron scattering started to become all the rage. But these compounds are difficult to look at no matter whether you're using X-ray or whether you're using neutron scattering because of the fact that hydrogen is super small. And tiny things are generally hard to find. And the idea behind this is if we look at just very generic diffraction experiment, if we're looking at X-rays, we're going to have some kind of X-ray wavelength coming in, impinging upon, and how X-ray diffraction works is these are going to interact with the electron cloud that's surrounding the atom. And once it interacts with that electron cloud, it's going to be diffracted by some angle, and then that's going to be compared versus theory. Now the problem again is that hydrogen is tiny. And so how many electrons does hydrogen normally have with it? 1. So if it's in a bond, it's got 2. That's a fairly damn small electron cloud to work with as far as being able to diffract X-rays. And the thing is that X-ray scattering is roughly proportional to those. So if you don't have a lot of X-rays, it's mainly they're just going to go right through. They're not going to hit anything. The other problem is that if we're talking about either really 8 hydrogens or 8 hydride species, those hydrogens are going to be relatively close contact to what is in all probability going to be a fucking massive metal, right? You're going to have this tiny little thing, and then there's this enormous planet, very similar to, like, say, the Earth and the Moon. One's going to be much smaller than the other one. And so that also complicates it, because you're going to have massive scattering from this metal. It makes it very difficult to find it as far as the hydrogen goes. So X-ray is normally not used to find hydrogens. What is normally used to find hydrogen is neutron scattering. So for neutron scattering, that looks at the actual nucleus. And in that case, it's a little bit easier as far as trying to be able to find the hydrogen. You get much better scattering, much better data from neutron diffraction as opposed to X-ray. So both of those were actually used as far as confirming the structure that was presented in this paper. So some earlier experiments. So again, this is from the 1960s. The initial X-ray determination of manganese, pentacarbonyl, the hydrogen. This analysis was done at -75°C. Why do we want to do it at such a cold temperature?
So they're not moving as fast.
Yeah, so you guys probably have seen isothermal bubbles in like various X-ray structures that you've seen. And those bubbles that are shown are generally trying to show all the movement that would be associated with a given atom. And so as we go to a lower temperature, that movement is going to become less and less, and so we'll be able to get better data out of it. The position of the hydride was inferred from this X-ray determination. Again, from what I said earlier, X-ray is going to be bad because hydrogen is so tiny. And so what you generally do is infer the position of the hydride based off of the geometry of everything else. And if the geometry is distorted, you can be like, oh, there's probably a hydrogen sitting there that's distorting things. So what they were able to do as far as this hydride analysis goes is to, so this was a little bit before the Kubas paper. This was work was done by LaPlaca, Hamilton, and Ibert, 64. What they were looking at again was this manganese species. And so there were two things going on. They did the X-ray determination, and what they found was that their X-ray structure looked like it was an octahedron. And so the idea was an octahedron has 6 points. So 5 of those points were going to be taken up by the CO ligands, and then that last point was going to be taken up by the hydrogen. So what they saw as far as the X-ray goes is they couldn't see this, okay? They can't see that with the X-ray. It's not good enough. What they could see was these guys, and what this showed was that these 5 carbonyls were all in what looked like a regular octahedron, as far as these 4 would be forming that square plane, and then this carbonyl would sit below it. They couldn't see the hydrogen, but they knew that there was nothing else there. So if there was nothing else there, then you would kind of expect that one of these COs would flip up and you would have a trigonal bipyramidal species, right? And so that's actually the 2 different ones that they were trying to refute, as it were. So the other thing that these guys were looking at, we're trying to get this structure, and so a lot of the people had proposed that this is what the structure looked like, that it wasn't this regular octahedron, that it was much more similar to this pentacarbonyl iron species. So they were saying that this paper was refuting what prior claims have been made in the literature, that this species was more trigonal bipyramidal. So that was done by IR. It somehow seemed to indicate that this had a trigonal bipyramidal species. But when they did the X-ray, when they did the X-ray analysis, they really found that it was this guy. So the people that were saying that it was trigonal bipyramidal, sorry, I'm being somewhat convoluted, they thought it looked like this before they had more data. So they thought it was also trigonal bipyramidal, and that this proton was just buried in one of the metal's orbitals. So you'll note that I have these guys set up in a typical trigonal pyramidal setup. The hydride then would just be sitting on the face of that icosahedral that would form. So it's a little bit buried into the metal orbital. So it doesn't affect the positioning of these guys. That was incorrect. It was supported by IR theoretically, but once they actually got the structure and saw that it was actually forming this kind of regular octahedral compound, they're like, oh, the IR must not be correct. So that was work that was done before. They were starting again to use X-ray and neutron diffraction as far as trying to elucidate some of these transition metal hydride compounds. So other than this manganese hydride pentacarbonyl species, another one that was structurally characterized around this time is this rhenide anion, is what it's called, kind of an interesting name. So it's this potassium salt, and so if you take away the potassium, that means that that overall rhenium hydride has a -2 charge on it. They were able to do the neutron diffraction, and so this is our rhenium central metal. And what they found that the hydrogens or hydride ligands formed were a trigonal prism. So we have 3 up top, trigonal. We have 3 on the bottom, trigonal. If you connect those guys, you form a trigonal prism. The other 3 hydrides were embedded into the faces of that trigonal prism. So 1, 2, and then this guy on the back side, 3. So it has 9 nearest neighbors. If you look at the oxidation of rhenium, if we're talking about ReH9 2-, what's the oxidation state of rhenium here? 7+. So again, T0, I'm not sure why we keep on having T0s. What's the total electron count? Ah, yes, 18. So as strange as it is, right, to have all hydride ligands, it's still trying to obey our normal 18 electron compound. What this is showing is an expanded view of this. So normally when you guys see X-ray crystallographic structures, it's normally of a single molecule, right? It doesn't show the expanded solid lattice. Since this is an ionic species, normally you can have interactions of both the cation layer as well as the anion layer. So if you guys look at these guys, if you want to look at it kind of at a diagonal. So this would be a layer of the anion. So there's one here. And then we have a layer of the cation. And so these guys represent the larger potassium balls. And then we would have a layer of our anion, and then again a layer of our cation, and then another layer of the anion, so on and so forth.